Okay, all right. So welcome back, everyone, and thank you for joining us. So today we'll be continuing. Before we continue, I want to start off with a technical thing that is called homework. So we're going to have two homework sets in this. Like I said in the beginning, we'll have two homework sets. So this will be homework set number 1. And what we're going to do with the homework is the following thing. So I'm not going to give you a set of exercises for you to solve. What I'm going to ask you to do is to group up into groups of 2 people. You can 3 if you really want, but it's better groups of 2 people. If you really want on your own, you can also do that. And each group will basically make up a question. So groups, okay, from 1 up to 3 people. The preferred number is 2. Each group writes 1 question. The material covered by the question can be anything from the beginning of the semester all the way to the end of this class. So we're going to do an NMR quantum computer today. We're going to finish that up today. So all the way up to that, your question can cover anything. It should be similar to the standard homework questions that you're familiar with. So just pretend that you're a TA. Okay, TA is a teaching assistant. And you're TAing this class and you have to write a homework set. So instead of having a TA and writing the homework set, you're going to be the pretend TA and write a homework set. And after you write that, you'll hand it in. So the group writes the question. You write a question plus solution to the question. Okay. The question should be solvable within under an hour. Okay, so if a grad student like you or an undergrad student in your class gets the question, they should be able to solve it within under an hour. Okay, and then you hand it in. Hand it in by, hang on, should be Wednesday morning next week. So that's December. So this will be December 2nd morning. So let's set 8 a.m. Sorry. My phone. Apologies. Close this. Okay. So hand that in. This will be 50% of the grade for that homework set. Okay. After you hand it all in, I will take the questions, group them up into 1 homework set, and distribute it to all the students. So then everybody can solve everybody else's questions. Okay. So 4 is solve all questions. Okay, and this will be another 50%. Now, I'm aware of the flaw of the plan in the fact that you're also writing the solutions. And so you can just ask your friends for the solutions for the questions. But this is a graduate course, or it's a mixed undergrad-graduate course. And the purpose here is to learn. Okay, so just make your best effort to solve the questions without asking your friends for the solutions. That's not the purpose of the homework set. Okay, are there any questions with regards to this?
Do we need to solve it as the group?
Yeah, you can write each person solves the questions on their own. You don't need to solve as a group. Each person solves the questions on their own. The group thing is just to help you come up with a nice homework set. It's easier to do it in groups. Also, if each person comes up with a question plus solution, you will have too many questions for a homework set. And I don't want to bog you down with too much homework. Okay,
thank you.
So that's the purpose. Okay. At the end, we want 6, maybe 7 questions total, no more than that. Okay. So then when you're solving, it doesn't take you 3 weeks. Any other questions about? Yes?
When do we have to submit the solutions?
This? Well, December 2nd, by the beginning of the week after this, I'll give you the question set after I verify that all the questions are good, nice and solvable, and there are no mistakes on that. And then you can have another week to solve all the other all the homework set. Okay, so about so it will be handy on the 13th. So the deadline will be December 13th. Okay, this will be the deadline for the solutions. Okay, so with that out of the way, we can continue. And last time remember we finished our classical spin in a magnetic field, our quantum spin in a magnetic field. We did an electric dipole in a classical electric field, and we saw all those dynamics. And then we started talking about an Nmr setup. And what we're going to do today is, one, we're going to continue with our Nmr setup. So I'm going to draw the setup in just a moment and finish explaining about that. After I finish explaining what an Nmr setup looks like, and you'll understand how to use it, we'll discuss about coherence times. So those are the finite time, the lifetime and the dephasing time of the nuclear spins. We'll discuss what coherence times means. And after we discuss coherence times plus how they're measured, how they are measured, I will show you how see how we can explicitly construct an NMR quantum computer. Okay. So explicitly how to run quantum algorithms on such a setup. So this is our plan for today. Okay, so let's go back to the NMR setup, and so I'm drawing the setup. This is what we had on the board last time. I will draw it and then I will explain again what we had. Okay, so this is the NMR setup, what we drew last time. Now this is very schematic, but you can understand any NMR setup in these terms at the end of the day. So what's happening here? This is our NMR solution. So there are molecules in here, and we'll talk about what these molecules are in a moment. But just think of an ensemble of nuclear spins. So we have a solution within a liquid. So we have a liquid solution with loads of nuclear spins. And this Helmholtz coil here provides us with some magnetic field B naught, Let's call this the z direction. So this will be the z direction. And all this setup is responsible for doing is generating RF pulses, okay, that will give us the transverse field to apply onto those spins. Okay, so a linear RF pulse, just like we saw in the calculations. And schematically, what is happening here is this. So this thing over here is just a generator. It is usually marked as a LO, local oscillator. I'm giving you these terms because they're also used in every other scheme. So when you talk about trapped atoms, ions, cavity QED, all these things, so this terminology will repeat itself in those systems also. So you'll have a local oscillator, which is typically set very close to the frequency that you expect the Larmor frequency to be, or the frequency of your qubits at the end. Here you will have a controller. This is called an AWG controller, arbitrary waveform generator. And what it does is it modulates through a mixer. So if you remember last time I showed you what these mixers do. And it modulates the local oscillator through the mixer such that we can get basically any arbitrary pulse we want within a certain band around the frequency given by the LO. So this gives us some frequency LO. Okay, so if we have, this is some frequency space and this is omega LO, we have some band, okay? This bandwidth is basically how fast this arbitrary waveform generator can work. Okay? If it gives us a pulse every nanosecond, then our band is a gigahertz. If it gives us it can change the voltage every millisecond, then this bandwidth is a kilohertz. Okay? And it sits around this, so it's being modulated around this frequency. This is what's happening here. This is just an amplifier. You usually need to amplify your signals. And what you're seeing here is a directional coupler. Oh, we're missing something like this. This directional coupler plays the role of a quasi non-reciprocal device. It's completely reciprocal, but the role is basically you want to route the signal into the sample, but the signal coming back, you want it routed onto the output. Okay? What is happening here in this device, maybe I'll draw it like this over here and explain. A signal that's coming from this port over here will mostly, 99% of it, come out of here. And a signal coming in from this port will come out of here 99%. Okay? But the signal that's coming in from here, 99% will go to this port, but 1% will go to this port. This 99% is not set in stone. It can be anything. It can be 90% and 10%. It can also be close to half and half. It depends on the coupling between these two transmission lines. Okay, so you can buy, these components anywhere, and you can have the ratio be whatever you want, from 50-50%, and then it's basically a beam splitter. You've heard of beam splitters, or it can also have a large ratio. Okay. Yeah. So what is happening over here? Basically, the signal is coming over here. Now, when you send in the signal into the NMR, you want a large signal. And you want the signal to come back mostly into your output port. And also, you don't want a very strong signal to come out and blow your amplifier and blow your electronics. So you're sending in a huge signal, and you want most of it to come out of here. So what is happening, the signal is coming here. Most of it is coming out of here. But some of it, 1% or a few percent, goes into the sample, gets reflected, okay, the RF signal gets reflected, it comes back here, and then a few percent returns over here, but that's negligible, won't cause any damage over here. Most of it will travel down here, get amplified, will go into this mixer, which is now down converting our signal, which is coming into this band. It is being mixed with this reference frequency over here. So it gets down converted. So most of the time it gets amplified again, and then it goes into a computer which can basically digitize the signal. Okay? So this is what's going on in the setup. Now, the spins in here, we're putting a big B field, so they're mainly aligned, or the magnetization, the overall average magnetization is aligned with the B field, and the AC field is being applied in transverse, so the spins will be oscillating this way. Okay? And if the spins are being oscillated this way, then this coil over here is going to be also picking up the signal. So for manipulation, you'll be sending in a strong pulse signal, and once the transients of this pulse go away, then you can actually pick up a magnetization signal coming from the processing spins. Are there any questions about this? Was this clear? Now is the time to ask. How many of you did the NMR experiment in lab 4? Just do a yes or no thing on the thing so it's clear to me. Wait. Okay, so about half of you. Okay, so that half I believe understands what I'm talking about. Are there any questions? No. Okay, so we're going to continue. And now that we've seen what the setup looks like, what we're going to do now is talk about coherence times, and then we'll see how we operate this thing. Okay? And what we're assuming here when we're talking about the solution for now is we're talking about non-interacting spins. So we have a large ensemble of non-interacting nuclear spins. Okay, so coherence times, and I'm going to write here phenomenology, okay? Because we're going to treat the coherence times in a phenomenological way. Okay? And the first question to ask is, what are coherence times? When we talk about coherence times, what processes do we talk about? Anyone? No? No one? Can I just not hear you, or you're not answering? No one's answering.
I'm not answering.
Hmm?
I think coherence time is the time that the spin not interacting particle, that the particle not interacting, or the spin stay like you prepared it.
Okay, so coherence times refers to basically the loss of, it refers to several processes that lose, basically we lose the information that is encoded in our qubit, okay? And in general, you can, in the quantum information language, okay, you can think about a bit flip, right? It's basically a bit flip error, okay? Or a phase flip. Okay, so a bit flip would take you from 0 to 1 and from 1 to 0. And a phase flip will take you from, let's say, 0 plus 1 to 0 minus 1. And any errors and any coherence times can generally be mapped onto those two processes for a single qubit. But in the NMR language and in more realistic systems, what we usually have is a two-level system, and this two-level system is not in general degenerate. There is a higher energy level and a lower energy level. And then in a natural way you will get two processes, one which is in the NMR language called T1, and this is energy relaxation. And it is when you have your two-level system, your quantum spin, and basically you lose energy through decay from 1 to 0. This is the predominant this is the predominant effect. You can also go from 0 to 1 through temperature and things like that, and eventually you will equilibrate. The second process that you have is what is called dephasing. And this is the process where you're basically losing the phase of your qubit. If you think of an ensemble, right? Remember when we talked about an ensemble of nuclear magnetic moments, or ensemble of qubits or anything, if you think about the Bloch sphere, or if you want in the classical picture, the magnetic moments, if you assume everything is uniform, then if you're in the equator, then there's a defined phase to your state. But now think of the whole ensemble, and if the spins are talking to each other or talking to the environment, they're getting kicked around. And their phases are getting moved, and they're no longer pointing in the same direction. So there's no defined phase for this whole ensemble. And this happens over time. And this is what is called a dephasing rate. You're basically losing your phase. This is the equivalence of you not being able to track the state of your qubit. Basically, let's say you started your qubit with a 0 plus 1 state, and then someone came and started playing with the system, or anything came along and started interacting and kicking the phase of the spin in an arbitrary way. If you think about the nuclear spin, someone can just come along and do what? Play with what parameter?
The magnetic field.
The magnetic field, right? If we don't know about it, and someone is just jittering around with magnetic field, we're losing the phase of our spin. Okay, it's going to be rotating at different frequencies all the time, and in the rotating frame, it just looks like it's randomly going to jitter around. And this is the dephasing rate. Okay. Now, in terms of how the quantum state is represented, the dephasing rate, you can think of it as the decay of the off-diagonal elements. If you remember the density matrix, right? The diagonal elements, these are the populations. Okay, so T1 would cause the population to transfer, but a dephasing event would cause the decay of the off-diagonal elements without touching the diagonal elements. So these are in general the two processes that we will see. And they have very good underlying physical reasons, so microscopic origins to all these things. And we'll discuss them in just a moment. But in a phenomenological way, you can just describe them by what are called the Bloch equations. So before even discussing where they originate from, you can simply write the Bloch equations and use, under certain assumptions, and use those to look at the dynamics. And the Bloch equations read the following way. So M here, this is the magnetization. So dmz dt equals gamma m cross b in the z direction. This is just the z component of the dynamics that we saw 2 lessons ago. And now we add, this is the phenomenological part that will be responsible for the T1, the energy relaxation, some m0, this is our steady state magnetization, minus mz as function of time divided by T1. And we can write the same thing for the 2 transverse components. The mx of t dt equals gamma m cross b x minus mx t over t2. And you can write the same equation for the y component. And I mean, you can already solve these equations in your head. You see that this equation just leads to an exponential decay on the time scale of t1. And you can see that these just cause an exponential decay of the transverse component, the xy component, on a time scale of t2. And the assumption here in this phenomenological model is that the decay is actually exponential. So we're assuming the decay is exponential, and we're just adding these parts into the block equations. And for an NMR system, this is a very, very good approximation. So I want to discuss a little bit about energy relaxation. To understand the source of it and why it happens. And then dephasing. Okay, so energy relaxation. And like we said, if we solve equation 1, then you will get the following solution. So this is a function of t. If you look at the magnetization as function of t, this is m naught. Suppose that you start at t naught with some magnetization, you will exponentially decay towards some m naught. Okay? And the question is, why is there energy relaxation? Anyone? Why do we even have energy relaxation? Why does the nuclear spin, why does the magnetization go from one state to the other? Why does it decay? Why does the qubit want to go from 1 to 0?
Because it's a lower, and it has a lower energy in the 0 level, so eventually it would want to go to the least energetic state.
Why? It needs some process to do that. Right? It needs somehow to couple to the 0 level in order to be able to go there. If you think about, the Schrodinger equation, if it's an eigenstate, it's just stay there. It's just going to stay there. Right? The Hamiltonian for the qubit started off with, being in the 1 state. It will just stay there. Okay? You need some coupling to some environment. The fact that we have energy relaxation is because we have an environment. Okay? And the environment can be anything. So any coupling really between the 1 and 0 state through anything will lead to relaxation. Okay? And it can be coupling to, for example, defects, other atoms, or phonons. any excitations that come along and can interact with the spin will give us some moment. Remember the dipole operator that we talked about? So some effective interaction that will give us the off-diagonal elements to cause a transition from 1 to 0. Okay. But what happens if we put, let's say we take an electric dipole and we put it in complete vacuum? Complete vacuum, the middle of space, and it just sits there. And you put the atom there, a two-level system atom, and it's sitting there in vacuum. You initialize it in the excited state. What's going to happen to it?
Nothing.
It will decay eventually.
Why will it decay?
Because it's interacting with the vacuum.
Exactly. Okay. Even if you put it in vacuum, it's going to interact with the electromagnetic modes of the vacuum. The vacuum is not empty. It has electromagnetic modes, and we're going to see that in the next chapter. But even if you put it in vacuum, it can emit. Okay, so there's some natural decay to any two-level system. By the way, in real systems, these effects you can deal with by basically trying to create cleaner samples. If it's NMR, make your liquid more dilute, make it more pure, and so on to get rid of these effects. Can you do anything to get rid of the effect of the vacuum? Suppose that I want to slow down the decay rate further than what the vacuum would give me.
Maybe reduce the electric fields and magnetic fields there?
There's vacuum. So there's just fluctuations of the electromagnetic field of the modes there. So you're going in the right direction. I'm trying to lead you there. What can we do, though, to this vacuum?
We can apply a specific magnetic or electromagnetic field that we can control, and it's very strong compared to the vacuum.
Not so much, because you think of the vacuum as a broadband spectrum. So it's hard. Whatever you put there, it will couple to something. So if I assume that the vacuum is a completely broadband spectrum, then it's hard to do, right? You're just adding more modes. So you won't be decoupling it. But what you can do, you can alter the vacuum. Do you know how to alter the vacuum? Suppose that you put... Sorry, who answered?
Gravity?
Gravity, no, not quite, no. Forget gravity for the moment. Just put two mirrors. When you put two mirrors, you create a cavity, right? And inside that cavity, your density of states is going to be lower. I don't know if you've seen it yet in one of the courses, the Casimir effect. Basically, you quantize the vacuum within two mirrors, and then you get a lower density of states. And then the atom that's sitting in between those two mirrors doesn't see the whole spectrum of light, it just sees the reduced density of states. It mainly sees the mode of it sees just the modes that these two mirrors allow. And if you set it up such there's maybe one or two primary modes, if the atom is not at that frequency, it has a hard time to emit. Okay? So you can play around with a vacuum using basically cavities. And this is relevant really to the fields of cavity QED, trapped ions, superconducting qubits. They all utilize this idea of putting atoms in cavities to help modify the density of states to inhibit emission. So we can alter the environment. So vacuum, cavities, or some other way of altering the environment. But at the end of the day, any hardware that you choose, any platform that you're going to build, will have some finite relaxation time. You really can't get rid of this relaxation time. Whatever you do, there is going to be some finite relaxation time. And this relaxation time can actually be calculated pretty well. So you can calculate the relaxation rate using the tool of QED. Okay? Quantum electrodynamics. If you take into account the right things, you can get pretty good predictions for the decay rates. And if you take this tool of QED and you assume what is called a Markovian environment, okay, so Markovian, let's say a broad band density of states, and you do the calculation, and you may have heard, the result, the Fermi's golden rule. You've seen it somewhere, right? Basically, you have the probability of jumping according to your density of states. So if you assume this Markovian environment, okay, then your exponential, then your decay rate will come out exponential. Okay, so you do this calculation, and if you take some course on light matter interaction, or some other QED course, you will do the calculation there, and you will see the exponential decay. So under these assumptions, under Markovian environment assumptions, QED, we're not going to do the calculation, but the QED calculation will give us an exponential decay. And this goes very well with observation. Now, this QED calculation that people like to do also takes some assumptions into consideration, and it takes some, and it is not exact. But it works. If you look at system, it works, and you see this nice exponential decay. But in fact, if you do the calculation through perturbation theory, and don't take some of the assumptions taken in this simple calculation, you will actually see that at short times, so we said that we have an exponential decay. So this is our exponential decay. Okay, maybe what you do discover is that for real systems, because there is some finite density of states, for real systems, the probability for jumping from the initial state to the final state at short times is actually proportional to t squared. So at very short times, this does not look exponential, it looks something like this. Now this is hard to see in many systems, definitely in a system like NMR, where everything is very weak. But real systems will have this region where the decay is not exponential. And I don't know if you've ever heard of this region. Does anyone know what this region is called? Anyone heard of this? No? This is called the Zeno region. Or the Zeno regime. Anyone know why? Anyone know of the Zeno paradox? No. Okay, so maybe we won't take a detour into this, but it entails an interesting consequence. It entails an interesting consequence that suppose that you're in this region and you're measuring really hard projectively, your system keeps projecting back. And you can actually inhibit the decay if you're measuring strong enough within this region. So if you're rapidly projecting the system on a time scale that is faster than this time scale, you can inhibit the decay. But only if you can get into this region. So for a pure exponential, this would not happen. And you can actually show this, and for those interested, there are many papers very pedagogical ones by Pascasio. So you can look this up. Quantum Zeno effect. It's called the quantum Zeno effect by Pascasio, and it has some nice, interesting physics for those who are interested. Okay. All right, but for all purposes, for NMR systems, almost all systems, we see an exponential decay in the energy relaxation. Okay, so that was energy relaxation. The second thing that we want to talk about are dephasing times. So T2. And we understood already that the dephasing time is basically the loss of phase. And in an NMR system, so dephasing, or T2. And in an NMR system, there are several ways that dephasing can occur. So one form of dephasing can happen due to basically what you said before. I don't remember who it was who said inhomogeneous. Did I write homogeneous correctly? I think so. Magnetic field. Basically, if you have your ensemble and each spin sees a slightly different magnetic field because your magnetic field is not perfectly uniform, then each spin is processing a little differently, and that just looks like dephasing. Okay. The same thing can occur from low frequency fluctuations. You can think of fluctuations from run to run. Suppose that your controller, right, that's controlling the pulses that's going in, it's counting time, but it's not counting time quite accurately enough, and it's causing noise. So every time it's sending a pulse, every time you reiterate your experiment, every time it's sending in a pulse, the pulse that's being sent is being sent at a slightly different frequency. But you don't know this. And this will also be a cause of dephasing. Also, if the generator, if the current source that's driving your DC magnetic field, if that is fluctuating, then your DC field will be fluctuating, and that will also cause. So in general, you can have these low frequency fluctuations. Another two processes that occur have to do with higher frequency fluctuations, and these are spin-spin interactions. So the molecules are, they're moving around. The spins have some dipole-dipole coupling. It's very weak, but it's going to create some interaction, some unwanted interaction. And there's also spin environment interactions, like we said, phonons. So phonons can take away energy, but they can also cause little frequency fluctuations. So spin environment interactions would also cause. And I wrote these 2, 4, and I wrote them in this order because we're going to divide these two into two different processes. These are characterized by low frequency, and they typically give a time scale which is marked as T2 star. I'm going to explain in a moment what that is. And this time scale is a longer time scale, which is usually called T2. And sometimes in the NMR language, this time scale of T2 star is called the free induction decay. So let's take a 10-minute break, because I can see it's 1:20 already. And then when we come back, we'll talk about how to measure what these times means and how to measure them. So the T2 star, T2, T1, Rabi oscillations, how to measure them physically on an NMR system. And then we'll construct from that an NMR quantum computer.